Let's see now what the properties and structures are of a couple of smaller cycloalkanes. So let's start with the smallest one, the cyclopropane, which we already said has an internal angle of 60 degrees, which is quite a distortion from the preferred tetrahedral angle for tetrahedral sp3 carbons of 109.5 degrees. And so this is a large angle compression that the system is exposed to. The reactions that open the cyclopropane ring are very exothermic. So getting to a structure that is now open is energetically favorable by quite significant 27 kilocalories per mole, because if you remember, the strain per CH2 group in cyclopropane was about 9 kilocalories. The source of cyclopropane's instability really lies in the poor overlap of its bonds. Because the angle between the atoms is about 60 degrees, the orbitals are not really overlapping as we've so far been used to in a head-on fashion. They're actually oriented at an angle. They overlap sort of side-on, as shown here, which means that their overlapping surface is smaller and the overlap itself is bigger. Finally, the torsion strain in cyclopropane is another significant source of instability. Again, as I've shown before, cyclopropane is fully eclipsed. So this would be a Newman projection of cyclopropane, from which you can see that there are multiple factors contributing to the instability of this molecule. Moving on to the next member of the class, cyclobutane. Torsional strain, the angle ring strain is about the same as for cyclopropane, but it's spread out over 4 carbons, so overall ring is more stable. And this is pretty intuitive because the angle distortion is now smaller. This is a 90-degree angle, and the distortion from 109-degree angle is just 19 degrees. However, the torsional strain is still a problem in cyclobutane. And in order to release some of that torsional strain, cyclobutane ring is puckered. What I mean by that is that it has this shape of a butterfly or wings, if you want to, where there is the eclipsing interactions are not as severe as they would have been in the planar structure. Now this puckering comes at a cost. This angle is no longer 90 degrees, but it's at 88 degrees. So it's actually, the angle strain is increased, but energetically things still work out favorably because that increase in angle strain is more than offset by the decrease in torsional strain. And so these two systems are not quite eclipsed. So it's sort of interesting to see how larger systems deal with their strain in a different way. Finally, moving on to cyclopentane, we encounter an interesting situation. So the internal angle of a pentagon is 108 degrees. So this should be virtually unstrained relative to the 109 degrees. But the problem with this comes when we actually look at the structure of planar cyclopentane. This is planar cyclopentane, and what I'm drawing, and it should be apparent pretty soon, is that even though there is no angle strain, there is a large amount of torsional strain. So this is 10 eclipsing interactions. 10 eclipsing hydrogens, which is now becoming the biggest problem here. And so in order to avoid that, the system adopts an envelope-shaped conformation. And of course, in this envelope, it's not only one carbon that is out of the plane, that they alternate, so the system is fluxional and each carbon moves out of the plane. And so what the overall Newman projection for cyclopentane becomes is something that is now relatively staggered, where we something else, sorry, this is not hydrogen, something that looks like this. And so this is now a system which had no ring strain to begin with, and but introduced a little bit of ring strain in order to avoid unfavorable torsional. So this is the interplay of torsional and ring strain in cycloalkanes that is very interesting. It determines their energetic stability. And we'll see really a classical and extremely important example of this interplay in cyclohexane, which is our next topic.